the topic at hand, which is harmonics and electric power, and really how they affect RMS, reactive power, apparent power. So again, review for probably many, a square wave or the sinusoids that we'll look at in inverter-driven electric machines are not perfect sine waves. In theory, a square wave is an infinite series of sine waves at different frequencies, basic Fourier decomposition. But we have a fundamental, which is kind of that carrier frequency, that main frequency, and then other frequencies which are imposed on top of it, which alter the total waveform shape. So we a lot of times will describe these waveforms as the fundamental and then some of the harmonic contents. But this is really important to keep in mind because each one of these harmonics, and granted, this is a perfect scenario again, has a phase between its voltage and current. It has its own element of reactive power. And those are getting added in, and those are getting added in, and those are getting added in. So when we talk about reactive power, we almost need to, also RMS values, we need to discuss the reactive power of what frequency band, the apparent power of what frequency band, the RMS of what frequency band. And this is the difference, and this is why filters become so important. Because if one instrument has a 3 kilohertz filter and one has a 30 kilohertz filter, you're going to see different values because these harmonics have their own phase distortion. They have their own reactive element. They have their own RMS element that's getting added into the total. That gets even worse when we look at switching. And again, we'll get there. All right, so let's look at an example. Again, this isn't switching harmonics yet, but this is a practical example just to instill these points. So I'm taking another current and voltage that I've kind of manufactured in our software just for example's sake, so I can operate in the ideal realm. So my current is, fundamental frequency, has an amplitude of 5, and I implement 5th harmonic and 7th harmonic with a given amplitude. Voltage is 10 volts plus a different amplitude of 5th and 7th harmonic. So we have strong presence of 5th and 7th harmonic. And we look at the waveform, and my current, is quite distorted. My voltage is quite distorted. But these are pretty realistic signals that we might see in a dirty system. And we look at the RMS value. We get 3.64 for current and 8.25 for voltage. This is that RMS calculation. Now, if we were to do the the RMS of just the fundamental value, we get 3.54 and 7.07 again. Same values we had last time. So we have to ask ourselves, which one am I interested in? Do I want the one without any harmonics? Do I want the one with the harmonics? So that's the question we need to ask is, I want the RMS value of what? So I'm leading to something which is the switching frequencies. But this is a question to ask, and this just introduces this basic idea of not all RMS values are created equal. It depends what our frequency range is. So now let's look at the power, instantaneous power. So the instantaneous power has that same frequency content. It's got that 5th and that 7th. I think there's a 30-degree phase shift in here. We see power reversals at the frequency rate of both of these. So we take these two frequencies, we phase shift them. We're getting harmonics in the power at the frequency rate of the voltage and current, which I find to be pretty exciting. And you can see we have this element of negative power, so we have that reactive power, but there's quite a lot of action here. Harmonics of the fundamental. So these harmonics introduce this distortion element. And what we see again is if we take the power factor of the total system, we get 0.827. If we take the power factor of just the fundamentally, again, that's 8.65. Which frequency are we interested in? And I think even more interestingly, if we take the power, so power is not immune from this either. If we take because the 5th and the 7th contain, the 5th contains negative power elements, the 7th contains positive power elements. If we take the power of the total frequency spectrum, we get 24 watts or 24.8 watts. If we take the power of just the fundamental, we get 25 watts. So there's enough negative power in the fifth harmonic that we're actually making a decent, 4% of the total power is going to that. So this is another circumstance where we'll have people tell us, like, we get a different power value with your instrument versus somebody else's. Well, if you're filtering out the fifth harmonic in one instrument but not the other, you will see different power values. Even if it's just a little bit, there will be a difference, because which frequency band are you looking at? And again, I'm not going through math. I'm giving practical examples. If you want to go through math, please hit me up offline. I don't like doing the dissertation thing. But this is a real issue of which frequencies am I interested in? Because in theory, if I took this signal and I filtered it down to its fundamental, I'm going to see more power than is actually being produced at the output of the inverter. So that's instantaneous power. Now, getting into kind of RMS and reactive power elements of this, we take the same voltage, the same current, but now we do our RMS calculations and we see, VRMS, IRMS. We do our power calculations, reactive power, apparent power, power factor. In this example, I think it was a 50 kilo sample rate, 50 kilohertz filter. And we go through the math, which is S equals V times I, RMS voltage times RMS current. We get 30. We take our power, which is instantaneous voltage times current averaged over a period. And we get Q by taking the Pythagorean difference of that to get 16.87 var. That's what we're measuring in this example. Now, if we go back to the definition of Q based off that power triangle, just that phase-based power triangle, we get V times I times the sine of theta, which is the phase angle, which if we take, 8.25 times 3.64 times the sine of 30.11, we get 15 var. Why is there a difference here? The difference is that phase angle is based on the fundamental. That phase angle is 0 to 0. But my signals have that fifth harmonic, that seventh harmonic, which have their own element of reactive power. They have their own phase alignment. So this V and I contain harmonics. We also need to account for the phase of those harmonics. We need to account for the power in those harmonics. So you can almost have to look at power factor in the circumstance with harmonics as power over apparent power. So that's another variable out there, which is, again, has that harmonic content in it if you leave it there. Okay. So now let's look at the fundamental, because fundamental is something that's very valuable to engineers. A lot of engineers ask for the fundamental, and we'll touch a little more on that. I introduced it earlier, but let's talk a little more about that. So the standard RMS and fundamental contain the harmonics. Each harmonic has its own RMS and phase. When we refer to the fundamental, we are referring to the first harmonic only. So if we take that first harmonic only, and we again do our calculation for VRMS, V fundamental, IRMS fundamental, we see that difference in value. Same with power, same with apparent power. So now if we look at apparent power, we have 30 in the wideband, or the no filter situation. We have 25 in the fundamental situation. So there's a big drop there. For reactive power, we have 16.87 var, which drops to 12.5 var in the fundamental situation. So this kind of traditional equation is dependent on V and I being calculated on the fundamental or one individual harmonic. Fundamental RMS removes all of that harmonic content. It takes the frequency, it looks at just that first Fourier series transformation. We actually have in our software a package for doing that automatically. So it extracts all those harmonics out. And we get the reactive power calculation to be, the same as we're calculating here. So you just really need to know what you're looking at. You need to know what you're calculating. These are math functions. They take what you input and they output something. So you need to understand your inputs. So fundamental is a really powerful tool for just looking at that fundamental main power carrying element. So if we look at, kind of the fundamental versus the unfiltered, and this is just a table highlighting what we've already seen. Q and S and the RMS values have components contributing from the harmonics. And the same data gives you different values depending on what you calculate. So filtering has similar effects. And now I'm going to give some examples with switching frequencies, with inverters involved, where now this becomes really, really apparent why this is such a big difference. Yeah, so also if we look at this, we can look at the power in that fifth harmonic, we can look at the power in that seventh harmonic. We can look at the RMS voltage and current in that seventh and fifth harmonic. And we can look at the reactive power and apparent power, because each one of these harmonics has their own elements of reactive power, of apparent power. So you can break it down to like understanding your values based on the harmonic content as well, which is a pretty interesting thing. If you're doing fifth harmonic injection, if you're doing third harmonic injection, you can start to understand the power quantities there, because it will affect your total output. So again, we just need to know what we're looking for. How many harmonics do we want included in these calculations?